but I think without wasting too much time, let's get started. So I'm super excited to welcome Moritz again to the show today with a deep dive on a step-by-step design workflow for creating a custom saddle using HyDesign. And Moritz is going to show you how this powerful tool streamlines the entire process from concept to the final product. So with the introduction out of the way, Moritz, stage is yours.
Yeah, thanks, Jousef, for the nice introduction, and very happy to be here again. Second time the charm, as they say. Hi, everybody. For the people that don't know me on the other side, my name is Moritz, Director of Engineering of Hyperganic, a software company based out of Munich with locations also in Singapore. We are focusing in the field of software. We're developing software for additive manufacturing, for generative design, and we aim to combine everything that we have, which is structural simulation, fluid simulations, and the complex latticing design software into the next generation of generative design software. I'm going to show you the first step on our journey towards that goal, which is HyDesign. And I'm very excited to showcase today a workflow of one of our customers, a user of HyDesign, who uses our product HyDesign to generate custom saddles, custom road bike saddles. So I'll walk you through that. I'll give you an overview over HyDesign, how it works. I'm going to give you also an overview over the simulation capabilities that we just very recently put into HyDesign, into our web-based tool, so that you can do structural simulations using our immersed boundary method solvers, which means you can do meshless simulations on the cloud. And then lastly, as a short outlook, I'm going to show you the logical consequence of having simulations and design within one tool, which is then, of course, optimization loops, integrated optimization loops between the two, and which shapes or forms this could take. So without further ado, here's the overview of HyDesign. Once you created your account, this is what you're going to see. Quick overview here. In the top section, you'll have the launch area, so where you get to the product HyDesign. On the bottom, you have a quick start guide, short intro, so that you can get started effectively running. So now let's launch. So I'm in the projects area. I see all the projects that my team and myself have created. In my case, these projects are all created by myself. I don't have a team here, but I could, of course, filter for my own projects. I can create projects as well. So let's create a new one. Let's call it Tech Deep Dive. And I hope I didn't misspell. Create a project, and here you go. We have the product outlook. You see the design canvas in the center here. We have all the geometric operations on the top bar. You can import and export objects here in this menu, hamburger menu. You can switch between design and simulate up here. I'm going to go into that a little bit later. You can create, of course, primitives, shelling, offsetting, constructive, solid geometry operations here, translations, rotations in the center, and of course, the lattices, such as beam lattices, TPMSs on the other side here, and all the modulations that one can do. Just a short hint before I dive into the deep dive for the saddle. The lattices of our dear partner ForwardAM you can find here with a link to the lattice library that I already pre-opened here on the side. Of course, you can see all of this is happening in the browser. So again, this is a web-based tool. So yeah, in the lattice library, you'll find all the lattices of our partner BASF ForwardAM or ForwardAM now that are also embedded within the tool. Great, so that's it about the outlook. Let's now dive into the success story of one of our customers, David, who created this road bike saddle with the help of HyDesign. So it took just a short moment to load the saddle. So as you can see, the saddle consists of multiple components. And I'll go through all of these components by themselves, little by little, and I'm going to explain a few words about the design choices made here. So let's go and get started with the forward AM lattices directly, which of course are one of the key features used here. So you can see that as the forward AM lattice library at the moment does not provide seating devices, or it does provide seating devices recently, but these seating devices are for car seats, so very large cells. We opted for selecting footwear lattices here, and you can see that the lattice unit cells are very uniformly distributed here throughout this saddle structure. You can see that the automated surface conformal lattices here create a nice conforming lattice texture on the surface. And yeah, one of the advantages here is if you print a saddle like this with powder materials, of course you want to elevate a product like this to a product final stage or product ready stage, so that you can sell your end product as fast as possible. And what the forward AM lattices here really helped doing is bring our customer to the effectively design ready stage relatively quickly. So what does this look like? If I select these forward AM lattices here on the side, I see the parameter window. And of course, here I could go ahead and change these to a different type of lattice. So just to reiterate on the seating, as mentioned before, I'll quickly confirm here and run the lattice change. And you'll see the change in the unit cell size as well as the beam thickness of the individual lattice beams. It's going to take just a short moment to update. And I don't know if you guys can see this. It is updated now. You can see that the lattice cells are much larger, which in our case here might have resulted in a saddle that is potentially too soft. So we wanted to have unit cells, or especially our partner David Medina wanted to have unit cells that are smaller, so you can fill the space more evenly. So let's go back, change back to the footwear lattices as originally used, and then move on to the other components of the saddle. In the meantime, just to highlight, of course, you could select also your own lattices, which you would do in the lattice fill menu here. I'll quickly show what that looks like. You have a wide variety of different lattice unit cells, and we're of course working on bringing in many, many more at the moment to really assist our users in latticing designs. Further, of course, the TPMSs. A handy feature about the TPMSs is you can effectively use these pre-existing TPMSs, these implicit functions that we have here, gyroids, S-surfaces, Swartz D, and so on, map them in different coordinate systems. Typically, you'd see that in Cartesian coordinates. And why don't I just quickly show that as well? I'll create a small cube just to illustrate what this looks like. So here we have the TPMS. You see all the objects that were already loaded in this project. I'll use a wall thickness of 1 Cartesian coordinate system. Let's use a cell size of 5 by 5 by 5. So we have our classical all-beloved gyroid. And now to just illustrate some of the functionality that is available to the user, such as the infills here, you can merge one pattern, which is here a gyroid, into a second pattern along a primary axis. So in this case, I'm gonna merge this into a Schwarz diamond along the x-axis. Confirm this quickly. Maybe increase the wall thickness slightly or decrease. That should do it, and open up the structure. Very nice. And you can see that there's a smooth blend between these structures. And now let's go even a step further and modulate this implicit pattern also along the x-axis, maybe with a grading factor of 1.3. I'll explain what that means in a second. So by 1.3, that means that the cell size is, in this case, the cell size is enlarged or is getting bigger along the x-axis here. So now that we have the technical descriptions out of the way, let's dive back into the saddle. So I'll toggle the visibility of our cushion again. Just a moment until the viewport updates. In the meantime, I'll toggle also the other components. So here we have the foam pad, effectively the cushioning of the saddle, the skin pad that typically is used so that the bike rider that is riding this saddle doesn't slide around too much, because of course you want to retain your seating position as well as possible. And let's show finally the inner skin. So a few interesting details about the other components here. Through the use of the TPMS infill, David, our partner in this project, could design a very high friction surface, effectively by infilling a surface pad here with a TPMS structure that allows the rider to have a good seating comfort and at the same time a nice level of surface friction. Of course, this is going to be enhanced even further by the printing process. So if you print this in powder, the surface roughness is also going to be a little bit higher. And then finally, all parts assembled. This is the ready to go part to be spat out onto the printer and then manufactured and tested ultimately. Last word to this before we dive into the structural simulations. Of course, you can export each one of these components by themselves or the entire thing once you boolean everything together. We support multiple export types such as STLs, decimated STLs, where you can set a relative error. So the higher the error, the smaller the file size. Of course, also the bigger the geometric deviations. 3MFs, shout out to the 3MF consortium, of course, for working on standards, PNG stacks, CLIs, and our native format HVX. So that's everything about the saddle. Again, thank you, David Medina, for providing the materials and your support. And I'm happy to see the first real success cases on our products. Right. So let's now dive into what the future beholds. I'll go right into the next example, which is a simulation case. And therefore, I'll use this bracket I somehow have an emotional attachment to this bracket. I use it for a lot of showcases, so forgive me if this is too boring, but I think it illustrates a lot of the concepts that we're working on quite nicely. So now I have designed this bracket, and now I want to simulate it. So I can do that, and as you can see, a modal shows up. This is in beta. I accept. You set up your simulation here on the right side. So in order to do that, you create a new simulation by pressing plus. You set up your boundary conditions by adding these in through the plus button here. You select, for example, the forces. You can create manually the boundary condition interfaces here, or you can even upload them as concrete faces if you want to. And then you run your simulation. As you can already see, there's one tick missing in comparison to the simulation tools that you're normally used to, which is the meshing. That for us, of course, doesn't exist. We can immediately move the geometry from the design stage into the simulation stage. So now let's go into the simulation results and show, for example, the one misses stress in this bracket. So this bracket experiences tension on the face here in Y direction. You can see the Y axis in green on the bottom. So it's normal to this face is tension, and it is fixed down to the bottom. This is a setup that I'm going to use for the next chapter of this presentation as well. So now let's look into the structure and get a sense of what this looks like and where the stresses really are. Sorry, that was the wrong direction. So you can see, of course, as you would expect, that the tension would act on this nose-like structure here. And rightfully so, you see the stress concentrations at these places. The key benefit now of having a immersed boundary method simulation tool is that, as you can surely imagine, if you needed to create a body fitting mesh as per typical finite element simulation methods, this would be a nightmare and would take ages. Whereas for us, this and for you guys, of course, this step wouldn't exist. And you can directly move from your design stage into the simulation stage. Last point to HyDesign before I move on to HyLight, a feature demonstrator where we trial things that we want to bring into HyDesign in the near future. If you like what you see, or if you would wish for an addition of features, please do request features up here on the right in the info box. Of course, also you find also links to the quick start guide and yeah, all the support you would need. Hopefully you'll find up here. Great. So I'll use the last few minutes and dive into HyLight, and then I'm open for you guys' questions. I hope I'm not overrunning time too much. You just stop me, Jousef.
You just keep going. It's fine.
Okay, great. So let's dive back into the bracket case studies here. So I used the same bracket as you've seen on HyDesign, but this time I used HyLight, which is our feature demonstrator for integrated geometry generation and simulation, and therefore optimization, to optimize the latticing structure inside. There are two ways that we currently implement, that we have currently implemented to optimize the lattice structure. One is to optimize beam lattices. So you start with a lattice structure that is too weak, and you iteratively increase the beam thickness in the areas of highest stress, so that the bracket overall becomes stiffer. And the other version is to leverage field-driven TPMS design, which is you use TPMSs or implicit fields to fill the space and then grade or modulate these TPMSs according to the simulation field. What that looks like, I'll of course show in just a second. In this case here, the optimization criteria, maybe I should show this before. The optimization criteria was to have a bracket where the maximum stress is below 150 megapascals. It is made of aluminum, and I allow the beams to be thickened only up to 4 millimeters. So now let's look through what this looks like. So as you can see, the lattice structure generally stays pretty much untouched, except for the regions as we were already seeing before in the other bracket, the areas of highest tension, which are in this nosy structure here in the front. It's the same load case as before. So I'm pulling effectively on this side and I fix the bottom. And due to that loading condition, of course, there will be tension in this region here. And so it shows, let me turn this so it's nicer to see. You can see that the lattice beams here have actually already doubled in size. Same is true in the back here, where there's bending and shear load on parts of these, and even tension load on some other parts of these lattice beams here. So now when we slice through the entire structure, you can see the final optimized result. Now let me show you also what this looks like in a TPMS world, where we use the field-driven design to optimize the structure. I think it shows now, great. So you see the von Mises stress experienced here is around 30 megapascals. It is slightly heavier in case you noticed before. The workflow is a little bit different, of course. And now let's look what I mean by field-driven design. I think most of the audience probably is quite familiar with the typical outlook of a gyroid, even if you recall also the cube that I just showed before. That is a normal Cartesian map gyroid. Now, using the field to grade the gyroid results in a very interesting behavior that really goes to show here. So you can see that the cell size of the respective gyroid unit cell is squished wherever there is high load, so high stress. So you can see that the cells here turned much smaller in comparison to the remaining cells. This has interesting properties, of course, for all sorts of applications. First of all, it's making the structure much more lightweight, but it is also a nice structure to be depowdered as long as there are no, of course, no powder enclosures, which in this case did not happen. The nice part about this too is, and this is why some of our customers opt to work with this software, is that you retain the functional surfaces while only changing the inner livings, so to say, of the object, and eliminating materials. This is quite relevant in industries such as molding or generally tool making, for example. And of course, another nice thing about these structures is, due to the ability to simulate thermal conduction, you can make very lightweight conductive plates or filler pieces into your heat exchanger, so that the heat gets conducted most effectively. So that leads me to the last point of my presentation. I want to show an optimized mold, so that you can see what thermal conduction looks like or what an optimized field for thermal conduction using a gyroid would look like. Of course, given the design constraints given to the optimizer here. So here you can see a mold, and I think this has also been part of the thumbnail. So now let's slice through this mold. I designed the mold, the gyroid here, to be a little bit larger, of course, so that people on also mobile devices would be able to see the structures better. So that's one of the design criteria that can be passed along. You can specify a min and maximum cell length, which of course has a direct influence on the weight and material consumption. What again is very interesting, this cup is experiencing a constant heat flux of, I think I set it to 400 watts, whereas the bottom surface here has a constant temperature, a typical scenario in molding. And now you would want to conduct this heat out of the structure as effective as possible. And you can see that wherever the heat load is the highest, the gyroid structure is also the densest. So especially here in the kink of the mold, you can see that you would expect thermal stress concentrations, and here, in fact, the structure is also the densest. So this porous structure, this gyroid structure, is here as dense as nowhere else in this mold. So yeah, that concludes it. Thanks, Jousef, for hosting me, and yeah, I hope you guys enjoyed it, and I'm open for you guys' question.
Excellent presentation. Thanks so much, Moritz. There was one question on YouTube. Can you modify a specific part to give the piece better resistance based on this simulation that you've shown?
Yes, let me go back into the bracket and potentially even walk through one of these optimization circles and just share it along the way we talk. So give me just a short moment. I'll bring up the window again. I hope I understand the question correctly. For example, what happens in this field-driven design here is that we take a normal gyroid and we make it stronger, so to say, in the areas that experience higher stress. So you would have a local refinement of this gyroid structure. So let me slice through into the red areas here, and I hope this came across. But this is, by the way, an excellent question. So this is the point of the highest stress here, and you can see that the gyroid cell size relative to the other gyroid cells is much denser. That means there's more material and therefore more stiffness in that region. So you have an automated local refinement or optimization of the structure.
Okay. Let's see if this answers the question. Maybe just please let us know in the comments. Thanks, Moritz. Regarding lattice design, you mentioned HyDesign's ability to handle lattice structures effortlessly. How does HyDesign's advanced lattice grading feature help in creating more efficient and optimized designs for products like saddles?
Yeah, so let's dive back into the saddle. I'll share my screen. I think I'm still in the, yeah. So let's bring up the saddle case study here, and I'll show on a rather extreme example what you can do. So it should become very obvious from that. So if I select the for the lattice here, and this of course is true for the normal lattice fill and also for the TPMS using the modulation, a feature that we are of course committing quite a lot of resources on and working to improve that a lot even further. So I'll load a modulation map, maybe this one here. So in the areas where I see white, the beam thickness is going to be changed the most, and in the areas where I see black, it is going to be changed the least. Of course, I can invert that, so now let's align the modulation map width according to our saddle design. So we have 250. Oh, hold on, that's the rotation. Sorry. 250. Even longer. Let's do it this way. 170. So now let's say in this case, I would be happy with my positioning of the modulation map. Of course, you can work with gray values in order to create gradients between black and white. I'm going to use this extreme example just to illustrate how the functionality works. So I'll use this modulation map. I have a starting stiffness number and a maximum stiffness number. In this case, I go all the way to the maximum. And now let's confirm and wait for the design to update. So in just a moment, you will see a change in the lattice beam thickness according to the gray values that I passed along with this image. So let's wait a second for this to update. Sometimes it's also a little bit difficult to see, but it should be visible. Let me unview also the other parts of the saddle. Yeah, it is a little difficult to see because already, since these are manufacturing driven lattices, ever so slight changes already have a significant impact. But you will notice that in this area here, you have thinner lattice beams. So you have the same lattice beams as per footwear A1, which is where you see the properties here. And for the remaining structure, wherever you saw white color, we have a footwear A4, which is this one here. And you can already see that the shore hardness is from below 27 to round about 40 to 55. Of course, this is a bulk property, but you can imagine that the modulated thickness is quite a lot stiffer in comparison. I hope that answered the question.
I think so. Very detailed answer. Thanks, Moritz. We have time for one more question. Let's see which one we pick. Additive manufacturing. HyDesign is focused on AM. Can you elaborate on how the tool expedites tooling design and production in comparison to quote unquote traditional methods?
Well, I think it is a use case specific, of course. Wherever you would want to use lattices, or wherever you would want to do more complex designs where your traditional, let's say, parasolid or solid-based CAD tools would run into limitations, that is really where HyDesign excels, and is also going to help you excel in your workflow. So, for example, if you want to create more lightweight molds by leveraging these lattice structures, if you want to optimize these lattice structures, of course, generally the entire topic of lattices, TPMSs, and everything that revolves around this space, that is something that is not typically part of normal CAD tools. And of course, there are, depending on the use case, many more applications that can be very useful. For example, the Booleans, very complex Booleans. If you have complicated surfaces, if you have multiple, so for example, double curved surfaces, or very, just very complicated surface structure, then typically in CAD, in normal CAD or solid-based CAD tools, you would run into issues with the Boolean operations. So this is another aspect about HyDesign that, to the best of my knowledge, the users that we currently have on the tool really love about the tool.
Mm-hmm. Actually, Light. So I want to have two more questions, Moritz, because they're quite interesting. One being, would you explain about the mesh generation process?
You mean the simulation mesh?
Correct. Yes, I think so.
Yeah.
That's what's
okay. Of course. I'll go back into the simulation case, and maybe I'll just show. I'll dive right into the simulation side. So if you look at this bracket here, let's go to the van Mises stress. So if you look at the bracket here, it has quite an intricate structure to its design. So in traditional CAD or in traditional simulation CAE packages, you would run this object here through a meshing process, which means you take the part and you fit a finite element mesh that is body fitted to your object. So that means all the simulation elements effectively are inside the solid structure here, and all the empty volume would also be empty ideally. As you can imagine, approximating a structure like this is going to take quite a lot of time. It is going to be quite compute heavy. So with our immersed boundary method, finite cell method, structural solver for, again, linear elastic static stress strain and thermal conduction, you effectively immerse the geometry into a grid of regular sized or irregular sized hexahedral simulation elements that then make so effectively it's almost like dissolving the object into this pre-existing simulation grid, and then we use the information of which elements are filled with object to simulate these simulation elements. Of course, there are rules of thumbs that we automatically employ because you can technically decouple the two. There are rules of thumb, like, for example, if you have a given wall thickness, you want to have a specified number of simulation elements inside that wall in order to make sure that you have a, in order to achieve convergence for your simulation. So of course that is an important part.
Mm-hmm. Great.
But since maybe one more word to this, but since we're looking at making this as easy as possible, we have done many of these things in the background for our users already. So for example, the convergence part to some extent is already taken care of. So you don't actually need to worry about that aspect, at least at the current stage of the product.
I also posted a link to our podcast in the chat so people can check it out. I think you explained in a little bit more detail how that works in the podcast so people can check it out.
Yeah.
And then last but not least, can you add a new topography?
A new topography? I'm not sure if I understand the question. I'm sorry.
Maybe you can specify in the chat. And then someone was asking, what is the blue, if you go back to the saddle, Moritz, what is the blue structure that we actually see? What's the color code of that blue
okay,
thing?
yeah, of course. Let me go back. Let's toggle visibility on all the parts. What is the blue structure? I think the blue structure, I think the question refers to the lattice structure here.
Correct.
I don't know exactly what topography is about, but you can, for example, generate a different lattice structure. So let me do that. I'll just select a the foam-based TPMS, and let's just create a TPMS-based lattice structure. So let's do just a brief example now. So yeah, here you go. So I could, for example, also use the gyroid now for the saddle, and then add the other components like the skin on the top and on the bottom here. And then, of course, I could do all sorts of other things to this gyroid. So I'll quickly just unview the skin pad on the top. And let's say I want this gyroid in the front, or I want it in the back, and I want another TPMS in the front. So I'll merge this, as I was showing before, into, for example, a sports diamond again. And I will use this infill. This is going to take a short moment to update. So now the gyroid is going to transform or linearly interpolate into a Swartz diamond pattern that potentially might be a little bit stiffer, even depending on the cell size, and then you can even modulate that further. For example, also again in X direction. Let's modulate it by some value.
Did you define any boundary conditions, Moritz, for this structure? Any loads, any boundary conditions?
At this stage, this is a sole design problem. Of course, I could, which goes again towards the field-driven design. You could, of course, specify a starting TPMS structure, and then due to the simulation load case, it would automatically do the grading for you. That is effectively what I've shown with HyLight, our feature demonstrator, which illustrates the next stages of our product. Really, the next few things that are gonna go live very soon for everybody out there wanting to try these types of functionalities.
Okay, I think people are very much interested in getting to know more details about hyperganic and HyDesign. So feel free to check out hyperganic.com if you have any more questions, or get in touch with Moritz via LinkedIn. He's very busy though, but give it a try. Try to add him as a new contact. And as I said, more information under hyperganic.com. I'll also edit the session, make sure it's available on demand on my YouTube channel. And with that, Moritz, any closing remarks from your side?
No, not much. Again, it's been a pleasure speaking with you, and of course, more importantly, also with everybody else out there. I hope you enjoyed the presentation, and up to the next one. Can't wait for the next stages.
Thank you so much, Moritz.
Yeah, thank you.
Alrighty.